What if I told you that materials exist today that are stronger than steel, but actually lighter than air? And no, this is not science fiction. These are supermaterials. And the secret to their incredible powers? Well, it's hidden at the atomic level.
Okay, let's just dive right in. What you're looking at here isn't a movie prop. It's a real nano device being held by an ant. This is the scale we're playing on now. We're literally building the future, one atom at a time.
So you can forget about just wood and stone. We are smack in the middle of a material revolution, designing substances with what you could only describe as superpowers.
First up, I want you to imagine a material that can almost think for itself. That's the incredible promise of what we call smart materials.
So what does that actually mean? It means these materials are kind of like tiny pre-programmed robots. They can sense a change in their environment, like heat or pressure, and then react in a very specific engineered way. It's basically technology that mimics instinct.
Let's meet the three main players. You've got shape memory alloys, which you can bend and twist all you want, and they'll snap right back to their original form with a little heat. Then there are piezoelectric ceramics, which literally generate electricity when you squeeze them, and magnetostrictive materials, which change their shape when you put them in a magnetic field. Wild, right?
Okay, so from materials that are smart, we're now going to go to materials that are just plain extreme. These next substances are pushing the absolute boundaries of what physics even says is possible.
To get our heads around them, we have to go nano. A nanometer is a billionth of a meter. This tiny, tiny scale is the playground where scientists are building the next generation of materials from the atom up.
And here's a perfect example: carbon nanotubes. Just picture a sheet of carbon that's only one atom thick, rolled into a perfect tiny cylinder. The result? A material that is hundreds of times stronger than steel and happens to be a phenomenal electrical conductor.
Now, from the incredibly strong to the impossibly light, I want you to meet aerogel. Get this, that number means it's 97% air, making it one of the least dense, solid materials on the entire planet. It's like holding a solid piece of smoke.
Yeah, they call it frozen smoke because of its ghostly appearance. But what's really mind-bending is that it's so light a flower can support it, yet it's also one of the world's most effective insulators. That combination of properties is exactly what makes it a supermaterial.
And then you have something called metallic glass. See, unlike regular metals where atoms are all in a neat little grid, here they're completely jumbled up. And that chaos, that's its superpower. It gives it this unique mix of strength and flexibility, so it can bounce like rubber but hit like a hammer.
So this all leads to the big question, right? Shape-shifting alloys, tubes stronger than steel, solids made almost entirely of air. How is any of this actually possible? What is the fundamental secret behind these superpowers?
The answer, as it turns out, isn't on the surface. It lies deep, deep inside the fundamental building block of everything we see, the atom.
Every single property we've just looked at, from the strength of that nanotube to the lightness of aerogel, it all comes down to two things: which atoms you're using, and, maybe even more importantly, how those atoms are connected to each other.
And that right there, that's the real magic, the connections. These are the atomic bonds, the invisible architects that construct our entire physical world. Now, the real stars of this whole process are the valence electrons. You can think of them as the little hands on the outside of an atom, reaching out to connect with their neighbors. They are literally the atomic glue holding everything together.
So, bonds come in a few different flavors, but we're going to focus on the heavy hitters, the primary bonds. These are the strongest connections, the ones that really forge a material's core identity. And it turns out there are three fundamental recipes for these primary bonds: ionic, covalent, and metallic. With just these three simple concepts, you can build everything from a grain of table salt to a flawless diamond. First up, we've got the ionic bond. This one is a simple give and take. One atom gives an electron away, and another one just snatches it right up. This electron transfer creates opposite electrical charges, and that causes them to snap together with this powerful attraction, just like tiny little magnets. Next is covalent bonding. Now, this isn't a transfer, it's a partnership. Here, atoms actually share their electrons, and that locks them together in an incredibly strong, rigid link. This is the bond that makes carbon nanotubes so strong and gives diamonds their legendary hardness. And finally, we have metallic bonding, and this is a total community effort.
The atoms all pool their outermost electrons into this free-flowing sea that can just move through the entire structure. That's exactly why metals conduct electricity so well. That sea of electrons is like an electrical superhighway.
So let's connect all the dots. This chart shows you exactly how that electron behavior creates the world we see. With ionic bonds, because the electrons are transferred, the atoms are locked in place. That makes them hard, but brittle. Give it one sharp knock and the whole structure can shatter. With covalent bonds, the shared electrons form this powerful, rigid network, which is why materials like diamond are ridiculously hard and take immense energy to melt. And in metallic bonds, that sea of electrons lets the atoms slide past each other. That makes metals easy to shape and, of course, highly conductive. You see, the superpower is in the bond.
And that brings us to the future. We're now learning how to engineer these bonds with unbelievable precision. So the real question isn't just what materials can do anymore, it's, as our control over the atom becomes absolute, what are we going to build next? The possibilities, truly, are as limitless as the atomic combinations themselves.